Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to the online lecture series of EE222 microcontroller systems. I'm recording this lecture after a long break of 1.5 years, and the only reason to start recording again was to complete the lecture series in which only 3 lectures were missing. So here I am today to record one of those 3 missing lectures. So without any delay, let's start with the topic. One of the topics that was missing in my previous lecture series was related to the input-output ports of PIC microcontroller. So in this course, we have been studying the PIC18 4550 microcontrollers, and here is the pin diagram of that microcontroller. For any microcontroller to interact with its environment or with other systems and with the user, the microcontroller needs to have some input and output ports. We already know that. So in this PIC18 4550, in the 40 pin package, we have a total of 34 ports that can be configured as either input or output. For a port to work properly, we must have an option to configure it either as an input port or as an output port. A single port cannot work as an input and an output port at the same time, and I'll tell you why. When I say the term port, technically each of these pins is a port where an input or output can be taken. But generally speaking or conventionally, we refer to a set of pins as a port that belong to a single register inside the microcontroller. So we can use these terms interchangeably. Now coming back to the point that why we have to configure a port or a pin as either an input or an output, but it can't work as both an input and an output at the same time. Let's consider this single pin RB7 that I want to configure as both an input and an output, but it can't be done, and let's see why. So first, let's consider that this pin is an output pin. So when this pin is an output pin, this means that some load will be connected to this pin that would be driven using this pin. So let's just connect a resistor and an LED that is a diode with this port. Now when I send a 1 to this output port, a 5-volt signal is produced and is output to this pin. So here ideally I should get a 5 volt. But am I going to get a 5 volt here? That is the question, because the internal circuit of this port will also come into the play, and the internal resistance of this port will come in parallel with this circuit. So the voltage being dropped at this point may not be 5 volts, but maybe lower than that. To make it further clear, let's remove this resistor and let's just connect an LED. So now what will happen? I have sent a 5 volt signal here, but we know that an LED drops roughly around 1.2 volts. So if I manually read this pin externally at a voltmeter, I'll get just 1.2 volts here. But I sent a signal of 5 volts or a 1 at this pin to the output. So this is the main reason that I cannot use this pin both as an input as an and an output at the same time, because next, after setting it as an output and sending it with a signal of 1 or 0, when I'm going to read this pin, it's not going to return me this same value, the same data. A 1 may be deteriorated into a 0, or a 0 may be pulled up to a 1 because of the external circuit connected to that pin. So the reading on that pin would no longer be valid reading. That's why we can only use a single pin as either an input or an output at a given time. So with this, let's move to the registers associated with the input-output ports of PIC18 F4550. So let's jump to the section number 10. Here we can see that there are 3 registers associated with each port of PIC18 F4550. And from now on, whenever I say port, I'll be referring to the single pin of this microcontroller. So these 3 registers are trace register, port register, and latch register. The trace is a short form of tri-state buffer. The tri-state buffer can control the direction of that port. So we will configure our port as an input or as an output by using a certain value in the trace register or by writing a certain value in the trace register. The port register is the actual value of that pin that we can read. So it reads the level of the physical pin that is actually outside that microcontroller and that is actually interacting with its environment and the other systems and the user. And the latch register is the output latch of this port. So why this latch is important? Talk about read, modify, write operations. To understand that example, to understand what are read, modify, write operations, when we say we have configured a port as an output port, we can see that this is a microcontroller and this is the pin. So I can send any signal to this pin that can be a 1 or a 0, and I can drive my load that can be an LED or can be a motor or anything with this signal. So let's just draw an LED again. So here we have our load connected to this pin. And my program is just sending some ones and zeros alternatively to this pin to toggle the state of the LED to let it blink. Now, the toggle operation itself is a read, modify, write operation. So when I write x is equal to not x or x not or x is equal to not x, what I'm doing is I am reading the current state of x, and whatever the state I have read, I am then complementing it and writing it back to the pin after modification. So this is a read first, modify, and then write back operation. And all of this operation is done in a single cycle. Read, modify, write operation. So now, as we discussed just earlier, that we cannot read the state of a pin when it is configured as an output, but we still have to sometimes read the state of the pin, even in the output, even when it has been configured as an output pin, we are stuck. We cannot read the direct state of that pin. So at that point comes the output latch register. So whatever we are going to write to the port is going to go through this latch register and is then written to the port register itself that is physically connected to this pin. So when we are going to read the state of the port when it is configured as an output port, it's going to read the state of my latch, not the state of my port. So in that way, I have a duplicate of what I have sent to my port already stored in my latch register. And that is not connected to the load and that is not connected to the physical world. So it is not affected by any loading effect. So its state would be what that I had actually sent as the output data. So here comes the latch register, and obviously when we have configured this port as an input port, so we'll directly read the input state of this pin through the port register, and we'll directly read the port register. So these are the 3 registers that are associated with each single pin or each single port of this microcontroller. And to make this all this happen, to let the user configure the port as the output port or as an input port, or to perform read modify write operations or any simple read and write operations, we have a complex circuitry that is connecting the input, the inside of that microcontroller, the registers, to the actual hardware pin of that microcontroller. And next, I'm going to tell you briefly about what that circuit is, what is its design, and what is its functionality, and how we can actually, when we say the trace register, when we say that the trace is equal to 1, makes the port as an input port, how it actually works at the hardware end. So now let's move on to the physical structure of each pin. Okay, next we are going to discuss about the physical structure of our input-output ports. We are not going to discuss the detailed circuitry, but I'm going to give you an idea that how your input-output ports function and what parameters you have to keep in mind while using them as digital input-outputs. So let me draw a general structure of an input-output port of PIC microcontroller. Okay, so this is the basic structure of your input-output port. You will find many different variants of this circuit and many more different complicated variants of this port in data sheets or in books. And to be honest, this is not the exact circuitry that is implemented inside the PIC microcontroller, but this is just the basic diagram to give you an idea how the port works. So this is your one pin of any single port, and this pin is connected to NMOS PMOS complementary metal oxide semiconductor pair. Here this is PMOS and this is NMOS, P MOSFET and N MOSFET. P MOSFET turns on when a 0 is given at the base or gate terminal, and the NMOS turns on when a 1 is given at the gate terminal. When a 1 is given as the input, PMOS will be off and NMOS will be on, and a 0 will travel from this ground to the output. Similarly, if a 0 is given at this input, PMOS will be on and NMOS will be off, and the VDD will be connected to the output pin. So in this case, we can safely say that if we want to make our port as an output port, we will give an output here at this pin that is coming from the microcontroller. If we give a 0 here, let me write it in a different color. If we give a 0 here, it will become a 1. And if, let's suppose, we are dealing this pin as an output pin, and this is your tri-state buffer and this is your input. So if this pin is an output, your tri-state buffer should have to be cleared to make it an
output. If this is 0, then here it is 0 and it is 1. So this buffer is enabled, and here we are getting 1. So a 1 will travel here. This will be on and this will be off. So PMOS will be off and NMOS will be on, and the ground will travel from this point to this point, and just ignore this one for the time being. So a 0 will be output on the pin as desired. If we give a 1 at this pin at this point and we want to send this one to the output pin, this one will come here. This will become 0 after passing this NOT gate. Tri-state buffer is still 0 because we are going to make this pin as an output, but we are sending a 0 to this output. This tri-state buffer will remain 0. Here it will become 1. So this buffer will be on again. A 0 will travel through this buffer. Here on both these complementary pair, it will be a 0 at the gate input. So the PMOS will be on and then NMOS will be off. So VDD will travel through the PMOS to the output pin, and a 1 will be shown at the output pin. Now if we want to make this pin as an input, we will make the tri-state buffer 1. That will put a 1 here and a 0 here. So this buffer will be off and this buffer will be on. So when this buffer is off, there will be a high impedance X or Z state here. So both of these PMOS and NMOS pairs will be off. So here there will be a high impedance state or Z state coming from this particular side. So it is good for us that there is a high impedance state because we are not going to output anything onto the pin, but we are taking an input from the pin. So this pin should not be connected to this side, but it should be connected to this side only. So whatever is here on this pin, whether it is a 0 or it is a 1, it will travel through this line, through this buffer because it is enabled now, and it will be read at the input side of the microcontroller. So this is the basic structure of your input-output port. What is the purpose of telling this at this point is there are some exceptions in the hardware architecture of PIC microcontroller, and one of the exceptions is the pin RA4. In the pin RA4, your complementary pair is there, but it is connected like this. So no VDD is connected here. It is an open drain connection. This means that once the pin RA4 is set as an output, we can send a 0 at this pin. We can output a 0 at this pin by sending a 1 here. If we send a 1 here through this NOT gate, it will turn on this NMOS and a 0 will travel through the NMOS. But if we send a 1 here and it will pass through this NOT gate and become a 0, so a 0 will be here. It will turn off the NMOS and it will turn on the PMOS. But there is no VDD connected to the PMOS. It is an open drain connection. So this pin will remain as a high impedance state. We cannot output a 1 at pin RA4. We can output a 0, but we cannot output a 1. We can take input of both 1 and 0 at RA4. We can output 0 at RA4, but we cannot output 1 at RA4. And now this pull-up resistor comes in. We should connect a VDD and a pull-up RPU, a resistor, to VDD, at this output pin. So if we are sending a 0, it will be a direct connection to the 0, and there will be a 0 at the pin output. But if we are sending 1, there will be high impedance and VDD will travel through this pull-up resistor. So if you want to use your RA4 as an output and you want to send a 1 at the RA4, you should connect an external pull-up resistor to that pin to pull it up to 1, because it is an open drain connection. And the last thing about this port design in PIC18 is that on port B, at port B, we have some internal pull-ups also. So this circuit is there on port B. Port B has internal pull-up resistors. Now we don't want pull-up resistors at any port if we have a complete complementary pair connected to VDD and ground, and if there is no issue at the output and input side. So why are we giving internal pull-up resistors for port B? By the way, these pull-up resistors can be manually connected or disconnected using a special function register in configuration bits. So we can either enable these pull-up resistors or disable these pull-up resistors using the pin RBPU